In 1946, British government bulldozers leveled the entire village of Charlton to the ground. Residential houses, farms, and pubs went under demolition for one single purpose: to lay a concrete runway 7,900 feet long. The infrastructure that cost British taxpayers a sum comparable to the price of building a heavy gun cruiser was intended for the takeoff of just one airplane. This airplane would spend 382 hours in the air, complete 164 perfect test flights, and kill not a single passenger. Its tail would not fall off from metal fatigue, its fuel tanks would not explode, and it would never appear in grim air crash reports. Yet it is this flawless piece of riveted aluminum, with a giant wingspan exceeding the dimensions of a modern Boeing 747 Model 400, that would become the most humiliating mistake in the history of civil aviation. The £34 million machine would sell not a single commercial ticket. The problem lay not in assembly defects, but in blind faith in the wrong mathematics. In 1942, when Nazi bombs were still falling on the industrial districts of London, head of the government committee, John Moore Brabazon, received an order to design the post-war British civil fleet. Moore Brabazon, an aristocrat and aviation pioneer, viewed future traffic flows through the lens of pre-war luxury, ignoring the dry economics of costs. In his picture of the world, non-stop transatlantic flights from London to New York were to become the aerial equivalent of ocean liners. The committee approved a specification that called for a giant pressurized tube with a volume of 25,000 cubic feet. Inside the fuselage, it was planned to place sleeping cabins, a full cinema, a bar, and a dining promenade. For 145 tons of takeoff weight, Lord Moore Brabazon allocated a quota of only 100 passenger seats, and this monstrous ratio of dead structural weight to useful commercial payload was financial suicide from the very start. Moving 145 tons of metal across the Atlantic Ocean in strong headwinds demanded unprecedented aerodynamic efficiency. Any air resistance forced the engines to burn extra gallons of fuel, and the additional fuel ate into the already meager commercial payload. The traditional layout, with massive engine nacelles hanging under the wing, created far too many turbulent eddies. The chief designer of the Bristol Aeroplane Company, Archibald Russell, faced an insoluble physical problem. He needed to obtain a total power output exceeding 21,000 horsepower, equal to the thrust of 36 modern supercars, yet keep the wing profile absolutely smooth. Russell adopted a technical solution that would later turn the maintenance inspectors of British Overseas Airways Corporation grey. He decided to bury all 8 huge radial engines completely inside the wing itself. And it was precisely this complex mechanism for transmitting colossal torque from the hidden recesses to the propellers that would become the time bomb that turned an engineering triumph into a pile of scrap metal. Archibald Russell looked at the drawings of a wing profile with a span of 70 meters and 1/10 of a meter. This distance exceeded the length of a football field and the dimensions of the future Boeing 747. To push through the dense layers of air, a fuselage containing 700 cubic meters of empty space required colossal thrust. Russell chose the Bristol Centaurus 20, 18-cylinder air-cooled radial engines. Each delivered 2,650 horsepower. 8 gigantic units together generated 21,200 horsepower. But they could not simply be hung on external pylons. The traditional layout created aerodynamic drag that forced the engines to burn tons of extra fuel, and fuel directly destroyed the paying commercial payload. Russell made a radical decision. He buried these steel consumers of high-octane aviation gasoline deep inside the root section of the wing. The engines stood at angles to one another, forming 4 paired sections. All this primitive mechanical power converged at one point, in a central gearbox weighing several tons. This complex transmission unit received torque from two independent crankshafts and delivered it to 4 pairs of coaxial contra-rotating propellers. From an engineering standpoint, it was a kinematic masterpiece. The coaxial propellers canceled out the reaction torque and provided ideal directional stability in the event of an engine failure during takeoff. Yet inside the wing, there formed a genuine thermal and mechanical hell. 144 cylinders produced a monstrous amount of thermal energy. To keep the engines from melting themselves and the load-bearing duralumin spars, Russell laid an intricate network of internal air intakes, controllable shutters, and massive oil coolers. Each isolated engine bay was packed tight, with thousands of moving parts, hundreds of meters of hydraulic lines, and thick cables squeezed between the primary structural members of the airframe. The metal vibrated continuously under maximum load, transmitting a destructive low-frequency rumble to the fuselage frames. The massive gearboxes demanded constant lubrication under extreme pressure. The slightest drop in oil pressure threatened instant gear seizure, rupture of the crankcase, and a catastrophic fire inside the confined space of the wing, where adjacent bays held thousands of gallons of flammable fuel. While Russell celebrated victory over aerodynamic drag, the Engineering Directorate of British Overseas Airways Corporation studied the maintenance schedules for this Leviathan. The contrast between the flawless wing surface and the harsh reality of ground operations proved to be a death sentence. Under the conventional layout, a mechanic rolled up a ladder, opened the cowlings of an external nacelle, and gained direct physical access to the cylinders and carburetors. To replace burned-out spark plugs on the Bristol Brabazon, a technician faced an exhausting journey deep into the structure. Engineers had to crawl through narrow, dark maintenance tunnels, past the sharp edges of the ribs, dragging heavy tools behind them. They worked in a cramped space saturated with toxic fumes of gasoline and acrid engine oil. Any serious failure requiring complete engine removal or major gearbox overhaul turned into a major surgical operation. Mechanics had to take off large load-bearing skin panels and use special internal hoists to extract the multi-ton unit without fatally damaging the entire wing structure. In commercial aviation, an airplane earns money only when its landing gear leaves the concrete of the runway. Every minute on the ground is a direct financial loss. The accountants of British Overseas Airways Corporation quickly translated Russell's brilliant engineering compromise into cold columns of figures. Scheduled maintenance of the 144 cylinders and 4 double transmissions hidden inside the wing quadrupled the standard ground inspection time compared with ordinary transport aircraft. The airplane risked spending long weeks in repair hangars over the slightest leak from a rubber seal or a microscopic crack in a pipe. Depreciation of the machine's colossal cost was spread across a mere 100 tickets sold. And now this was joined by astronomical bills for hundreds of extra man-hours of work by highly qualified technicians. The ideal aerodynamics, for which maintainability had been sacrificed, did not offset even a small fraction of these costs. Add to this the world's first hydraulic power boost control system, moving the all-metal control surfaces with areas of dozens of square feet at a speed of 250 miles per hour by the pilot's muscle power alone, was impossible. The innovative system worked flawlessly, but its massive pumps, rigid copper pipelines, redundant circuits, and heavy fluid pressurized to thousands of pounds per square inch added several more critical tons to the airplane's empty weight. The scale of the machine produced a geometric increase in mass, and every extra pound of weight destroyed potential profit without return. Heavy copper wiring bundles running the length of the fuselage, thick duralumin skin designed to maintain excess pressure inside the vast cabin, and ultra-strong landing gear legs consumed what remained of profitability. The pursuit of technical perfection turned the machine into a financial monster. The rigid logic of detailed drawings defeated the physics of airflow, but surrendered completely to the merciless mathematics of transportation. On September 4, 1949, Chief Pilot Bill Pegg climbed the tall aluminum boarding stairs into the belly of the world's largest landplane. Behind him, there were neither the sleeping cabins, nor the panoramic cinema, nor the bar counters promised by the project. Throughout the entire colossal fuselage, with a volume of 25,000 cubic feet, reigned the cold emptiness of an industrial laboratory. Instead of 100 wealthy passengers enjoying cocktails over the Atlantic, Pegg carried behind him 1,000 measuring instruments. A web of hundreds of miles of thick copper cables snaked along the bare duralumin frames, rigidly connecting strain gauges on the wing spars to complex oscilloscopes in the center of the cabin. Massive recorders absorbed second-by-second readings of vibrational loads, hydraulic pulsations, and temperature differentials inside the hidden engine bays. Mounting this complex instrumentation alone required thousands of man-hours of technician work. It was not a luxurious Skyliner, but a 145-ton test rig for metal fatigue. Taxpayers paid £34 million for an illusion that on paper promised unheard-of luxury and turned out to be the echo of engineers' footsteps on bare, ribbed floors. Bill Pegg settled into the left seat in the cockpit, whose width surpassed the dimensions of a standard London double-decker bus. Directly ahead stretched the concrete runway 7,900 feet long, for the pouring of which bulldozers had leveled the village of Charlton. Pegg placed his hand on the 8 throttle levers and smoothly advanced them. Deep inside the 230-foot wing, 144 forged pistons came to life simultaneously. 21,200 horsepower poured their monstrous torque into the complex transmission gearboxes. 8 coaxial propellers roared and bit into the damp autumn air. The low-frequency rumble passed through thousands of riveted skin panels, but thanks to the Leviathan's colossal mass, vibration in the crew cabin remained minimal. The machine, with a maximum takeoff weight of 145 tons, lifted heavily from the concrete with frightening mechanical grace. The first fully hydraulic booster system operated flawlessly. Pegg did not have to fight the aerodynamic resistance of the huge all-metal control surfaces. The heavy, non-flammable fluid, pressurized to thousands of pounds per square inch, did the heavy work for human muscles. Every movement of the ailerons generated enormous loads on the center section structural members, but the ingenious lever system compensated for the deformations. The historic flight lasted exactly 25 minutes. Upon returning to Earth, the chief pilot recorded not a single hydraulic failure, not a single drop in oil pressure, not a single pulsation in the transmissions. The giant piece of metal flew flawlessly. In June 1950, the Bristol Brabazon passed with a deafening triumph over the runways of London's Heathrow Airport, and a year later demonstrated its power at the Paris Air Show in Le Bourget. Crowds of spectators gazed spellbound at the sky, convinced they were seeing the flagship of the future air fleet of the British Empire. The enormous silver silhouette, slicing through the air at a cruising speed of 250 miles per hour at an altitude of 25,000 feet, seemed an indisputable embodiment of British engineering genius. But while the morning newspapers printed rapturous headlines, in the offices of the Ministry of Supply and at the headquarters of British Overseas Airways Corporation, a brutal collision with reality was taking place. Profitability was measured not by loud applause from the crowd, but by the cost of every gallon of fuel burned per ton of useful payload. The airline's financial directors and analysts looked not at the flawless contours of the fuselage, but at the cold columns of commercial operating metrics. They already knew precisely what was being carefully hidden from the jubilant public. This perfect mechanism would never enter regular passenger service. Economic mathematics had delivered a verdict that left no chance of saving the project. To grasp the true scale of the impending financial catastrophe, the leaders of British Overseas Airways Corporation only needed to divide the airplane's takeoff weight by the number of tickets sold. 145 tons of alloyed aluminum, copper, and steel had to rise into the air, burning tons of aviation gasoline in order to carry just 100 people across the ocean. To achieve break-even on a flight, tickets for the Bristol Brabazon would have to cost 3 times more than those on competitors' flights. But even that sky-high price could not have covered the monstrous costs of maintaining the radial engines hidden inside the cramped wings. Every extra pound of weight inexorably took precious pounds sterling out of the carrier's pocket, turning the transatlantic route into a budgetary black hole. Lord Moore Brabazon's elitist concept, which naively assumed that air travel would remain the privilege of a super-rich aristocracy demanding private berths on board, shattered against the laws of the market. The new reality demanded extremely dense seating arrangements and high flight frequency. While the single flying prototype methodically accumulated its 382 test hours, competing engineers were already testing jet turbines and designing light, narrow fuselages capable of carrying twice as many passengers with half the empty weight. Physics worked perfectly, but the machine's economic model was dead before its landing gear first touched concrete. In 1952, the chairman of British Overseas Airways Corporation, Sir Miles Thomas, sat at the head of a long oak table in the company's London headquarters and looked at the final technical report. In front of him lay the detailed drawings of the second version of the Bristol Brabazon. Engineers of the Bristol Aeroplane Company were trying to save the sinking project by replacing the heavy and extremely complex piston engines with the latest Bristol Proteus turboprop power units. It was assumed that the light gas turbines would reduce the weight of the empty structure, simplify the nightmarish internal maintenance of the units hidden inside the wings, and raise the airplane's cruising speed to 400 miles per hour. On paper, the turboprop giant looked like the last real hope of recovering the millions of pounds sterling invested in infrastructure and development. Inside the giant assembly shop in Filton, under a roof covering 8 acres, the riveted skeleton of a new, enormous fuselage was already taking shape, into which hundreds of tons of scarce, alloyed duralumin had gone. But the dry financial analysis that the corporation's chief accountant placed on the table in front of Miles Thomas left no room for illusions. Even with the new engines, the giant airplane remained hostage to its absurd concept. Replacing piston cylinders with rapidly spinning gas turbine blades had not changed the machine's fundamental flaw. 700 cubic meters of pressurized volume were still intended to carry a tiny handful of people. Sir Miles Thomas took a fountain pen in his hand and drew a line through the most expensive British aviation project. He officially notified the Ministry of Supply that British Overseas Airways Corporation categorically refused to purchase either the piston-engined first model or the unfinished turboprop second model. This was not an act of sabotage. It was an inevitable capitulation before the harsh laws of economics. By this time, the de Havilland Comet was already roaring through the sky, the world's first commercial jet airliner. It weighed 3 times less than the unwieldy 145-ton Bristol Brabazon, sliced through the stratosphere at 500 miles per hour, and carried a tightly packed load of 36 passengers, delivering incredible commercial turnover per flight. The future belonged not to luxurious flying palaces with sleeping cabins, but to narrow duralumin tubes with dense rows of seats in which people were willing to endure cramped conditions for the sake of speed. American engineers on the other side of the Atlantic, at the Boeing Corporation, were already sketching the contours of the future Boeing 707. This revolutionary machine, at a comparable takeoff weight, would be able to carry up to 189 passengers, fly twice as fast as the British piston-powered giant, and forever take the profitable transatlantic traffic away from ocean liners. Thomas understood perfectly well. If the corporation put the Bristol Brabazon on the prestigious London-New York route, every flight would generate colossal net losses. The airline would simply go bankrupt, paying the enormous bills for high-octane fuel and the amortization of the unique coaxial gearbox components. On July 17, 1953, Minister of Supply Duncan Sands rose to the dispatch box in the House of Commons of the British Parliament. A heavy, tense silence fell over the chamber. Politicians who had earlier, with enormous pride, allocated budget tranches for the construction of the world's largest passenger airplane waited for the report. Sands, without raising his voice and without resorting to emotion, delivered the dry verdict. He stated that the government was terminating the Bristol Brabazon program entirely. £34 million, taken from the pockets of British taxpayers in a war-ravaged post-war country, had been written off irrevocably as a pure state loss. Not a single commercial passenger ever climbed the steps of this aeroplane. Sands coldly explained to the members of Parliament that further investment in the project made no sense whatever, since the intended customer, British Overseas Airways Corporation, had categorically rejected the machine, and no airline anywhere in the world had been found willing to buy this flying financial vacuum cleaner. The minister's speech did not last long, yet it officially recorded the historic moment when the British aircraft industry realized that a perfect engineering model could be completely dead from a business standpoint. The most complex transmission, the flawlessly operating hydraulics, and the unsurpassed aerodynamics of the giant wing proved useless in the face of a simple fraction in which the numerator contained enormous operating costs and the denominator contained the number of passenger tickets sold. In the damp October of 1953, heavy trucks and crews of industrial metal cutters arrived at the concrete airfield in Filton. The single flying prototype, which only recently had drawn admiring crowds at the Paris Air Show, was rolled out onto the cold apron. Workers started the compressors, switched on pneumatic shears and heavy gas cutters. They began methodically destroying what had been the pinnacle of Archibald Russell's engineering thought. Sharp steel blades bit into the thick duralumin skin, forever tearing apart the perfect aerodynamic profile of the enormous 230-foot wing. The complex, massive central gearboxes, for which first-class technicians had crawled for days through the toxic confines of the internal engine bays, were roughly torn from the load-bearing spars and dumped onto the oil-stained concrete. Hundreds of miles of costly copper wiring, vibration-strain sensors, and precision measuring instruments were thrown onto piles of industrial waste. 8 giant Bristol Centaurus 20 radial engines, each rated at 2,650 horsepower, were sent to government storage as spare parts, while 145 tons of high-grade aircraft alloy were sold to scrap processors at the price of ordinary secondary metal. In the neighbouring giant hangar, the half-assembled skeleton of the second turboprop version met exactly the same brutal fate. The point of no return had been passed, finally and irrevocably. Lord John Moore Brabazon's vision of a luxurious aerial ocean liner turned into a shapeless heap of cut aluminium. The only tangible legacy of the £34 million remained the colossal concrete runway, 7,900 feet long, on the site of the village of Charlton, that had been erased from the face of the earth, and the giant assembly shop covering 8 acres. By a cruel twist of fate, this massive and extremely expensive infrastructure proved highly useful. Decades later, it was from this thick concrete that British supersonic Concorde airliners and heavy strategic Vulcan bombers would take off. The Bristol Brabazon project was ruthlessly wiped from the face of the earth, leaving behind only the cold, mathematical conclusion about the end of an entire era. Whitney Straight, managing director of British Overseas Airways Corporation, hated illusions. In 1950, his desk was piled with dry reports on fuel consumption. Lord John Moore Brabazon's project called for a non-stop transatlantic flight, yet the physics of the atmosphere over the North Atlantic imposed harsh conditions. At an altitude of 25,000 feet, the jet stream prevailed, a dense flow of opposing westerly wind exceeding 100 miles per hour. To punch through this wall of air, the 145-ton Bristol Brabazon had to deliver maximum cruise power. 8 Bristol Centaurus 20 radial engines, hidden inside the cramped wings, ran on high-octane gasoline. Each of the 144 pistons required continuous injection of the mixture. Cooling the cylinders inside the enclosed wing demanded complex air intakes that created aerodynamic drag and forced the engines to burn extra fuel. Whitney Strait's mathematics painted a catastrophic financial picture. To cover the distance from London to New York, the airplane had to lift dozens of tons of fuel into the air. The fuel occupied an enormous volume in the wing tanks and consumed the lion's share of the maximum takeoff weight. Out of the 145 tons of the machine's total weight, less than 10% remained for the paying commercial payload, passengers and mail. 90% of the energy was burned simply to move the duralumin structure and gasoline across the ocean. The engineering tragedy lay in the square-cube law, which chief designer Archibald Russell could not override with brilliant drawings. The government committee's requirement to create spacious halls with a volume of 25,000 cubic feet inside the fuselage forced the designers to increase the diameter of the airplane's cylindrical tube to 16 feet. At high altitude, atmospheric pressure drops by more than half compared with sea level. To prevent passengers from losing consciousness from hypoxia, compressed air had to be forced into the cabin by heavy compressors. The difference between the high internal pressure and the rarefied external environment turned the giant fuselage into an inflated metal balloon. The larger the diameter, the greater the tensile stress experienced by the skin. Russell had to use thick sheets of alloyed aluminum and massive frames capable of withstanding the colossal cyclic loads during every climb and descent. The metal added tons of dead weight. If the engineers had reduced the fuselage diameter to the cramped dimensions of future jet airliners, they would have saved tens of thousands of kilograms. But the specification demanded ocean liner comfort. As a result, the Bristol Brabazon became hostage to its own volume. Every square meter of internal luxury was converted into extra kilograms of heavy, load-bearing structures that forever destroyed the economic viability of operation. The only sphere in which the scale of the Bristol Brabazon worked to the benefit of world aviation was the rigid mechanics of control. A machine of such monstrous weight and wing area required, for the first time in history, the complete abandonment of direct muscle linkage between the control yoke and the control surfaces. The aerodynamic resistance of the massive all-metal ailerons at cruising speed was measured in tons. Chief pilot Bill Pegg would have been physically unable to alter the flight path. Engineers of the Bristol Aeroplane Company developed the world's first fully hydraulic power boost control system without mechanical backup. This was a true engineering triumph hidden beneath the thick skin. Powerful piston pumps drove non-flammable fluid through dozens of meters of rigid copper lines. Pressure in the system reached thousands of pounds per square inch. When Bill Pegg moved the yoke, he only opened precision spool valves, while the actual force work was performed by massive hydraulic cylinders. But this innovation created a deadly problem: a complete absence of feedback. The pilot could not feel the density of the air, and with one sharp movement of the yoke could exceed structural loads and tear off the wings. To prevent destruction of the airframe, the designers had to integrate an artificial feel mechanism for the yoke, simulating aerodynamic resistance with stiff springs. These developments became the gold standard for heavy jet aircraft. But this breakthrough did not save the project's commercial insolvency. British Overseas Airways Corporation coldly calculated the cost of every hour of flight. The piston engines, overheated gearboxes, heavy hydraulics, and the enormous dead weight of the empty fuselage made operations unbearably expensive. The Bristol Brabazon was not a means of transport, but a flying financial paradox. It possessed advanced systems, but used them to serve an outdated logic of pre-war luxury. At the same time, pragmatic rival engineers had bet on gas turbine jet engines, which were more compact, lighter, and more reliable than complex piston units with their rubbing parts. The turbines consumed more fuel, yet allowed flight at twice the speed and at considerably greater altitudes where air resistance was minimal. Speed became the principal commodity in the passenger market, not excess space for strolling. When the heavy gas cutters destroyed the metal on the cold concrete at Filton, they were destroying not merely an airplane, but an entire economic paradigm. £34 million had become the price of a harsh historical lesson. British aviation had learned, once and for all, the rule that the laws of aerodynamics are inseparably linked to the strict laws of accountancy. An engineering solution without commercial profitability is doomed to end its days on a scrap heap, regardless of how flawless it appears on the drawings. In 1952, the Vice President for Engineering Development at the American Boeing Corporation, Edward Wells, spread out on his massive desk in Seattle the detailed drawings of the wing of the British Bristol Brabazon. Wells, who had designed heavy strategic bombers for the United States Air Force, was searching for an uncompromising formula for a transoceanic passenger airliner. The British drawing, with its 8 radial air-cooled engines buried inside the wing profile, provoked in him a cold, professional bewilderment. Wells calculated the ground maintenance time required for this monstrous assembly. To extract a single Bristol Centaurus 20 engine from its cramped internal bay, British aircraft mechanics would have to remove thick, load-bearing duralumin skin panels, disconnect a complex system of exhaust pipes, and separate the multi-ton central transmission gearbox. That meant many days of unprofitable downtime on the concrete apron. The American engineering concept that Edward Wells was at that very moment embodying in the secret Boeing 367-80 project, the prototype of the future legendary Boeing 707, rested on an entirely different industrial physics. Wells took the heavy Pratt & Whitney turbojet engines out of the wing's load-bearing structure and suspended them on external aerodynamic pylons. The increased frontal drag of the massive nacelles was more than offset by the enormous thrust of the turbines, yet any ordinary mechanic with a basic wrench gained direct physical access to the compressor blades within minutes. A simple engine change took a few hours rather than long, exhausting weeks. While British engineers tried to preserve ideal laminar flow at the cost of maintainability, the Americans made a ruthless bet on speed of servicing and maximum daily flying hours. Edward Wells understood perfectly that a commercial airplane generates direct losses every second it spends in the hangar, and his external pylons permanently solved the problem of access to the units. While aircraft engineers argued themselves hoarse over the placement of power plants, the president of the powerful airline Pan American World Airways, Juan Trippe, coldly counted the money. Trippe tightly controlled the most profitable transatlantic routes and viewed the British government project solely through the prism of the cost per passenger kilometre. In the Bristol Brabazon's technical specification, Trippe saw only a 145-ton riveted aluminum structure that burned thousands of gallons of expensive high-octane aviation gasoline simply to move 100 people across the Atlantic Ocean. In the mathematical reports of his financial analysts, this monstrous ratio of dead weight to useful commercial payload spelled inevitable bankruptcy on the very first scheduled flight. Juan Trippe had no intention of selling tickets to a spacious cinema above the clouds. His pragmatic business model demanded packing the maximum number of people into the smallest possible pressurized cylindrical volume. Trippe aggressively invested in narrow fuselages without luxurious promenades, sleeping cabins, or onboard bars. The Boeing 707 he ordered, at a comparable maximum takeoff weight, carried up to 189 passengers. Juan Trippe forced the designers to remove every unnecessary bulkhead, reduce seat pitch to the absolute minimum, and use light duralumin alloys to create a dense passenger capsule. Thanks to its enormous cruising speed of 530 miles per hour, The American jet airliner could complete 2 full round trips across the Atlantic in the same time it took the heavy, cumbersome, piston-powered Bristol Brabazon to struggle through just 1. The difference in commercial utilization was 4-fold. Juan Trippe coldly killed the illusory concept of aerial ocean liners with a single stroke of his fountain pen on a multi-million-dollar check to the Boeing Corporation, mathematically proving that the post-war market demanded nothing but mass transportation. Meanwhile, in Britain, chief designer of the Bristol Aeroplane Company, Archibald Russell, desperately tried to salvage £34 million of government investment. He initiated a second radical variant, the turboprop Bristol Brabazon Mark II. Russell made the difficult decision to discard the temperamental piston engines and install 8 paired Bristol Proteus turboprop power units in the same wings. The new gas turbines were considerably lighter and delivered far greater useful power, yet the physics of the rigid structure originally laid down would not permit correction of the fundamental error. The basic architecture of the giant fuselage, more than 16 feet in diameter, remained unchanged. Russell could not physically reduce the pressurized internal volume of 25,000 cubic feet without completely redesigning the entire airframe structure from scratch. This meant the new turbines would have to expend colossal thermal energy simply to keep pushing an enormous empty space through the dense layers of the atmosphere. The reduction in engine weight slightly increased the useful commercial payload, but the Ministry of Supply's finance department placed before Russell the merciless columns of calculations. The turboprop giant still lost catastrophically to American narrow-body aircraft in raw profitability. Fatigue in the alloyed metal of the massive frames, caused by the constant cyclic pressurization of the huge cabin, required the external skin to be thickened, which once again consumed every kilogram saved by the turbines. The mechanics of the enormous coaxial propellers, driven by high-speed turbines through complex reduction gearboxes, remained an absolute nightmare for maintenance. Archibald Russell remained shackled by the original flawed specification of the government Brabazon Committee, which proved to be a heavy slab of concrete around the neck of British aviation. The final act of this protracted engineering drama played out not in the skies over the Atlantic Ocean, but in the quiet offices of the accountants of British Overseas Airways Corporation. The head of the Fleet Strategic Planning Department sat silently, staring at material fatigue graphs and price lists for transmission spare parts. British heavy industry had spent an entire decade creating the perfect aerodynamic profile of the giant wing, completely ignoring the harsh, cold reality of daily hangar maintenance and pressurization cycles. The ruthless decision to send the single airworthy prototype under gas cutters for scrap at the price of secondary aluminum alloy was the most logical and justified financial action the British government took throughout the entire life of the project. The aluminum skin sheets, precision steel gearbox shafts, and copper hydraulic lines were quickly melted down. The village of Charlton, mercilessly bulldozed from the face of the earth to allow this 145-ton Leviathan to take off, was never rebuilt. British taxpayers had fully paid for the construction of the colossal reinforced concrete runway, exactly 7,900 feet long, which for years remained the most expensive monument to a design error in Europe. Yet the cruel irony of economic reality was that this very ground infrastructure outlived the destroyed airplane itself. 15 years later, the thick reinforced concrete at Filton Airfield would bear the colossal loads of the landing gear of the first prototypes of the supersonic Concorde. The Bristol Brabazon became a sad victim of a bygone era in which officials and engineers naively believed that status and comfort could defeat the laws of thermodynamics and market economics. Commercial aviation rapidly turned into an industry of millimeter clearances, minimal operating costs, and maximum seat density, forever closing the door on flying palaces.